Now it is the second part of the section 7.4. In the first part, we defined grow faster, grow slower, but these terms are a little bit ambiguous. Here we'll define more specific terms so that if the terms are said, then everybody can understand what they are. Let's see these definitions. The ratio f of g, the limit as x approaches infinity is 0. And then earlier we said that f grows slower than g, but we now try to say that f is of a smaller order than g, and we try to write down this condition in this way: f is little o of g. Once it is shown, then we can understand that in this way. Here, that means that f is growing slower than g, so that in order is f has smaller order than g. You may consider f and g are polynomials, so that once g has larger degree, larger order, then as x approaches infinity, g will grow faster, so that the ratio will become 0 as x approaches infinity. Okay, that condition can be expressed by using f is little o of g. Now here, the ratio is now bounded by m for x sufficiently large. But that one means that even you are taking limit x approaches infinity, here that is bounded by m, then we say that f is of at the most the order of g as x approaches infinity, and we write the condition in this way: f is big O of g. Okay, this condition implies two cases. F of g can approach to 0 or can approach to L here. Either way, they are bounded by m. If you choose m larger than L, then it's true. So here, this condition implies that and that one. That means once f is little o of g, then automatically big O of g, right? Okay, let's try to solve these problems. True or false as x approaches infinity. Okay, by using the definition, we can say is true or false. Okay, here start with now limit x approaches infinity. F is 1 over x plus 3, and then now g is 1 over x. But this is the same as x over x plus 3. Once x approaches infinity, then we know that this is converging to 1. Of course, it's always less than 1, and then converging to 1. So here, we can say that 1 over x plus 3 is big O of 1 over x, but not little o, so it is false. Okay. Now, here, part B, and again, the same limit. X approaches infinity, and square root of x squared plus 1 over 2x. Okay, if we divide by x, top and bottom, then it can be written here. That is 1 plus 1 over x squared and over 2. And here, that one is now converting to half. Right? So, and it's bounded by half anyway. That is always smaller than equal to half. Smaller than half, and limit is half. So that this condition is satisfied. And then here we can say f is big O of G. So it is true. Okay. Okay, part C, the same way. Limit x approaches infinity and f x logarithm x divided by x squared. Now that is same as logarithm x over x. We know that x grows faster than logarithm x, so that the limit must be 0. So here, this condition is satisfied. So we can say f is little of g. Okay, here. So it is true. Now, how about this one? So we'll ignore that portion and try to write down only the fraction. Logarithm and logarithm of x and divide by logarithm of x. Okay, as x approaches infinity, the top and bottom approach infinity. So from this one, by using L'Hopital's rule, here, okay, derivative of top is same as 1 over logarithm x times 1 over x. Derivative of bottom is 1 over x. So it is the same as 1 over now logarithm x. As x approaches infinity, we know that that is approaching 0, right? So this function is little o of logarithm x. Once it is a little o, then automatically big O, so it is true, okay? Okay, so far we dealt with the functions growing and here to infinity. Now we are dealing with functions converging to 0. So we start with a function, g over h, and limit as h approaches 0, the limit is 0. And along with g over h, we'll try to compare the behavior of f of h. So here, f of h over g of h in modulus is 0 in limit. Then we say that f over h is in little o of g over h as h approaches 0. So here, we may write down that way. Or we are using set inclusion notation, and we say that way. Here, the main thing is a little o. So once you see either this one or that one, then that means that this condition is satisfied. And here we are using, sometimes some people are using that notation, and over there also the same, rather than equal, and some people are using set inclusion notation for these two. Okay. Now, also, here the ratio in modulus is bounded by k, a positive number. Then here we say f of h is in big O of g of h, and we are using here that way, or we can write down in this way. Okay. Anyway, that means again that here the ratio approaches 0, so that again little o means automatically big O. Right? That means that once little o, then f of h is converging to 0 faster than g over h. And here, in this case, at least same order converging to 0. So that over here, once it's growing, then And we can say that it's at the most. But here, in this case, and we can say at least the same order to converging zero. Okay? Okay, show that these assertions are not true. Okay, start here, part A. So limit x approaches 0, and here e to the x minus 1 over, now g over h is, now g over x is x squared. You can see that here top and bottom approaches 0. So by using L'Hopital's rule, we can say this is e to the x over now 2x. Top is approaching 1 and bottom approaches 0, so that the limit must be infinity. So it is not true. It's not bounded, so that it's not true. And part B, here the limit, again the same way, x approaches 0 and absolute value of x over arctangent of x. Now top and bottom approaches 0, so that again we can use L'Hopital's rule, and then that one is top, okay, top becomes 1. Top becomes 1, and here bottom becomes 1 over 1 plus x squared, right? So that this whole thing is same as 1 plus x squared. So it is converging to 1. So it is not converging to 0. So we cannot say that it is in little o. If it is changed into big O, then it will be true. Okay, part C, again, same limit and absolute value of now sine x and cosine x divided by x. Okay, that one can be written in this way. Okay, for simplicity, we can combine them. That will be half of sine 2x divided by x, right? Again, top and bottom approaches 0, so that by using L'Hopital's rule, we have here, that one becomes cosine 2x, and bottom is 1. So here, as x approaches 0, it is approaching 1, right? So here is in big O, but it's little o, so that is wrong. Okay. Prove that arctangent of x is x plus big O of x cubed. You can solve this problem here two ways, as given here. The first one is, now if you are moving x to the left side, then you have to show that arctangent of x minus x is in big O of x cubed as x approaches 0. So that let's here now limit x approaches 0 and arctangent of x minus x divided by x cubed and absolute value. Now as x approaches 0 and top and bottom approaches 0, so we can use L'Hopital's rule, the same limit, and absolute value of that is 1 over now 1 plus x squared and minus 1 divided by here 3x squared, right? Now as x approaches 0, 1 minus 1, okay, it becomes 0, again 0. So that one more time, we can use L'Hopital's rule. But before that, okay, we reorganize on the top, or we can do it anyway. Here, that is now Okay, so that is minus 1 plus x squared and power minus 2 and times here 2x, right? The derivative of top is given in this way, and bottom, that is here 6x, right? Okay, so we can cancel this 2, and we can rewrite the term in this way, limit, and of course 1/3 can go out, and then now that is, okay, you may ignore also minus sign, but anyway, that is 1 plus x squared and minus 2 power, and we can cancel this x and x, and 1/3 equal out, and that is 1 here, right? As x approaches 0, then top becomes 1, bottom 1, so that limit must be 1/3. So here, we start with this, the fraction, and we take limit x approaches 0, and we reach at a number, and a bounded number, so that big O is true, right? You can do it in this way, and secondly, you can do it in this way. Okay, here the hint is given that derivative of arctangent is 1 over x squared. Once absolute value of x is less than 1, but we are thinking the condition as x approaches 0, so that we may assume that x is satisfying this condition, then we can write in this way, 1 over 1 plus x squared is the same as that. So that here, and we take integration, integrating both sides, we can reach at here now, arctangent of x is the same as, okay, that one is x. Now minus x squared is changed into 1/3 of x cubed. And then the next term is 1 over 5 x to the 5 and minus, so like that. Once x is smaller than 1, it's true. Okay, that is true. So that here, for that portion, remainder portion, we can say that that is order big O of x cubed, right? You can easily check that once this portion is divided by x cubed, then that will only 1/3 will be remained, and other part has at least x cubed, x squared, so that it is approaching 0, right? So we can say that here arctangent of x is x plus big O of x cubed. Either way, you can prove that. Okay, for this problem, f of x is here 1 plus h e to the minus e to the h. What are the limit and the rate of convergence of f of h? Okay, what is the limit? Well, here, f of h, so that limit h approaches 0, then that is 1 plus h minus e to the h. So 1, the limit is now 1 plus 0 minus 1, so that limit is 0. And here, we try to see the rate of convergence of f of h. This problem is asking you to find the largest k such that f of h is big O of h to k. Okay, in order to get k, here we start with the definition h approaches 0, and then f of h, 1 plus h minus e to the h over h to k. And absolute value. Now, for that one, and once h approaches 0, then top and bottom approaches 0. We already know that. So by using L'Hopital's rule, here that is 1 minus e to the h, and that is k times h to the k minus 1. Now, this one is approaching 0. And also, if k is larger than 1, then now it is approaching 0. So that here, we may assume here now k is larger than 1 here. And so that we can find, because we have to find the largest k. Okay, then bottom and top approaches 0. So here now, by using L'Hopital's rule again, it's the same as, okay, e to the h, in fact, minus e to the h, but you don't have to put minus because we are checking only the modulus. Okay, that one is the same as now k and k minus 1, and here h to, oh no, yeah, h to k minus 2. Right? Okay. Now, so the limit must be bounded. Some number, okay, so that some k, then we have to choose k, we are using k again, so it's a little bit confusing. So let's try to say this is L. So we have to choose k such that this quotient as h approaches 0 is bounded. Okay. Top is a constant converted to 1, and bottom is this constant times that one. So once k is, for example, 2, then now this one, if k is larger than 3, larger than 2, so that, for example, 3, then it is approaching 0, so that the quotient will blow up. So that once k is 2, then now that one is 1, so that eventually this becomes a constant, right? So that the possible largest one for k is 2, okay? So that eventually we can say that f of h is big O of h squared. Okay, that's the end of the section. Thank you.